Well, hello. This is a lecture on design, explain what design is and how it's been done in the past. This is primarily in support of the RED project from NSF. My name is Gary Tatterson, and it's August 2017. And we're going to talk a little bit about design here. The first thing you should recognize, design tends to be vague, a little bit on the vague side. Needs some sort of definition. Interesting term. And the RED project is supposed to develop something new and innovative in the way of teaching design. And some of the material here may contribute to that sort of innovation. The first thing you should recognize about design is there's extremes in design. And on one side, you have conceptual design. You might want to call that innovation. As opposed to that, you have engineering design methods, right? Established engineering design methods. Or you can think of it as the Wright brothers as an example of conceptual design versus the Ford Motor Company being established designs. The important point here is the Wright brothers did not have a design manual for an airplane. That may seem a bit obvious to you, but maybe it's not so obvious. The second thing about the Wright brothers and their efforts, the technical data at the time was wrong. The published scientific literature was wrong. Oh heavens, the scientific literature being wrong, how is that possible? Anyway, what we have here is a graph. We have conceptual design versus incremental design, and we're going to claim that the Wright brothers is an example of conceptual design, and Ford Motor Company is dull, boring, repetitive design. Now, design, conceptual design is all about attempts to get a working process or getting a working device or whatever. In that area, you're going to have an awful lot of failures. So it's going to fail. And it took Wright brothers 4 years to actually develop the airplane or their flying machine. You turn around and talk about DuPont with the TiO2 process. They developed the TiO2 process, and basically it was a TiO2 process was basically a bomb, right? And they had a number of explosions, and they always rebuilt their equipment to try again. Eventually, they figured out how to do it without having any explosions. So the TiO2 process inside DuPont is basically a controlled bomb, all right? Anyway, a few people over here, Wright brothers, maybe what, two brothers, and then you had maybe one or two support. Lots of attempts, lots of failure. As opposed to that, we can have the Ford Motor Company over here, right, incrementally chugging along. This would be incremental increases. You have to say that the Ford Motor Company designs automobiles, but you must also recognize that they start with an existing design and improve that design. So this might be considered incremental design. Not much pizzazz, although I like to think of it as being new, right? But the designs might be because of new government regulations or a new twist in what the customer wants. Over here you have Ford Motor Company I guarantee you was a huge bureaucracy. Designs, small changes in design may have to be approved at various levels of management. So you have a significant time lag. Over here, Wright brothers could make changes overnight, right? They didn't have to go through any sort of established methods. Now, what's interesting, I find this interesting. What people think? Well, always. Everything available now has always been available. That's what people think. They're not accustomed to not having it, and they conceive that it was always there since the beginning of time. For instance, we take the ballpoint pen. You would figure that it was probably around during the Crusades and during the flood. Anyway, no, the ballpoint pen was developed. It maybe around 1910. At that point, it was entirely new. The design problem was trying to get a ball to be in a pin-type configuration to be able to withstand an impact. So everybody with a ballpoint pen is going to start doing that to it, and you don't want it to break. So ballpoint pens, when they first came out, were about $15, I think. Anyway. The reason why, you may ask, why isn't this in PowerPoint? Well, let me explain something to you. There you go. See, you can scribble on your screen here quite quickly. And PowerPoint, that's not, that function is not available. Anyway, that's why this is not on PowerPoint. This is the old-timey method. Well, conceptual design, again, can be called innovation. Design is the process by which something is made, developed, specified, etc., etc., etc. That something is the end objective of design. You can divide design up into engineering disciplines. You can have electrical designs, you have chemical designs, or chemical process designs, or product design, not product designs down there. You can have mechanical designs. Design can be divided into other categories, like product design versus process design, right? Or conceptual design versus incremental design or final design. Actual design never ends. It's sort of like an artist painting a picture. Artist is never completely finished with painting a picture, and the design process actually never ends as well. Anyway. So, product design is a major subject, right? And product being maybe a car or a cell phone. Now, what's very, very important is needs. And to be quite blunt with you, we could say needs actually define the process. Once you have established what you need, the design is relatively easy, or at least that's my opinion. I suppose you could find examples where that's wrong. So you really ought to spend a lot of time thinking about what is it you actually need. And then the very important issue in design is going to sell. You're going to make money at it to justify your design, and that's extremely important. Usually you run into the business types of people who want to rush to market. They have something, they want to rush into production immediately so they can get the marketplace first. Now, that's a great idea, but it's also very hard on design engineers. So I consider you do a two-prong attack. You rush to market with your product, and at the same time then do the engineering, design, and design improvements. Let's get back to this needs idea. Case in point, you're told to make red plastic, so you're going to make some red plastic. You want to make some red toys, maybe a red fire engine, right? So you're told to make red plastic so you can mold them into fire engines for toys for little boys and girls. So you go ahead and put red dye into plastic, and lo and behold, you have a red plastic, and you go into production. Now, at the end of summertime, all that red suddenly is pink. Have you ever seen red toys over the summertime turn pink? It's a very common occurrence. So upper management now thinks, oh, geez, pink fire engines, just really not a great idea. And it's a really ugly sort of color. So the needs changes. The need is not red plastic anymore, but it's red plastic with color durability, right? So you have color durability sitting here. Okay. This process, putting dye in plastic, is pretty simple. Not difficult at all. But when you have color durability, it usually means putting a pigment, which is a solid powder of sorts, into plastic. Now that's a difficult problem, first-class pain, and it's not easily done. The equipment putting dye in is not the same equipment that you would want to use to put pigment into plastics. So here you have needs. The need was fairly simple, dye, the design was fairly simple, off-the-shelf type of thing. And over here you have maybe a processing problem, getting pigment dispersed. So we get up here, and the process design, what's that? Well, you're going to make a batch of cookies, maybe chocolate chip cookies. So you got to figure out what steps you're going to take and in what order you're going to do it. And lo and behold, you got chocolate chip cookies. So that would be, you got to buy the chocolate chip cookies. You got to get the butter and the flour and the cooking baking soda. You got to get them lined up, and how you're going to mix the stuff. Maybe you throw in a couple eggs, large amounts of butter, and then you figure out what the process is. That's what chemical engineers do when they do process design. We're figuring out what steps are necessary to take. In design, you have what I call you pick. Students are not accustomed to such freedom. You make choices in design. Okay, making choices in design. You don't making choices in design. The other thing, so students are not accustomed to such freedom as to making these choices. And then we have design does not have one single right answer. Actually, there's many different answers out there for design. Okay. And this really bothers students a lot. You can take a look at the number of cars out there. You get an idea that design of cars is a whole bunch of different types of cars, so different designs. Students are accustomed to having one right answer. In high school algebra class, you had your problem, you write the equations, and you solve the equations. And there was one right answer. In design, there's many right answers, right? Some are good designs, provide good products. Some are fairly lousy designs that don't work very well. Designs need to be reasonably correct. They need to be flexible, robust, versatile. They need to be nimble as well. And I'll throw in this easy for design for easy cleaning, inspection, replacement, and repair. So those are some of the items that our designs need to be. Right. Whether it's a product, whether it's a process. Now, what really happens in chemical processing, you already have the equipment existing, and you take your process and force fit it into existing equipment. You don't have necessarily the advantage of designing the equipment, the new equipment, from scratch. You use the old equipment. Now then, among design methods, right, we toss out some classical design methods here. The first one, probably the best example of that, would be Kern's book, Process Heat Transfer. And this was before computers. Yes, there was a time before computers. Oh, heavens, how can people live today without computers? Where design was done with pencil, paper, and slide rules. And Kern's book, 1950, is a very good example of design. I just happen to have Kern right here. A picture of Kern process heat transfer sitting here. And if we open it up anywhere, you find here, for example, the calculation. We're on page 284. Go to the library, you probably find Kern on the shelf. Calculation of a butane de-superheater condenser type thing. All right. So you obviously it has heat transfer going on, and in this case you have available equipment, and so you design what you need and compare it to what you have, and then away you go. But if I take a look at this, I have go back here, point down in there. I have shell side calculations and tube side calculations. This is the type of equipment, shell and tube heat exchanger. It has an outside tube, outside shell, and lots of inside tubes. And if I turn the page, I can see quickly that basically I have very detailed calculations here and very detailed calculations there. And standard procedure in calculating this thing. Away I go. At the very end, I check to see how much area I have versus area that I perhaps need, and see if I can use that piece of equipment for the process. Then I might go in and recognize that I need pressure drop and do pressure drop calculations. I need pressure drop because pressure drop times volumetric flow rate is power. It gives me an idea how much power I'm going to use to run this condenser over a period of a year. And I can go through here. These are all excellent examples of, here we have the calculation of ammonia compressor aftercooler. I'll tell you, you can't hardly beat Kern. It gives you a sense of security. Look at all that. And away you go. Isn't that fantastic? Now, like I said, this is 1950, right? Classical design methods, process heat transfer by Kern. Now, this is the book that beat Hitler during World War II. Thought I'd point that out to you. The design techniques given in Kern was used to design heat exchangers during World War II. I'm quite sure about it. And as a result, Hitler lost. And if I take a look, open up Kern here, we got Copper's Company. And we see Kern was adjunct professor, and he was process engineering type guy for Tatterson Foundry and Machine Company. Okay. And this particular edition is the first edition, second impression. And I think you could probably see here it's 1950. And this is an extremely excellent example of old-timey design, so to speak. Old-timey design. Let me move that back up here. Now, opposed to detailed calculations, lots of things don't necessarily lend themselves to calculations. Considering heat transfer is easy, fairly easy. As a result, it's lots of ways of designing a heat exchanger. Lots of equipment tends to be less able to do calculations. So the alternative to detailed calculations would be simply a table lookup. And we have Wallace's book, fantastic book. I think this came out in 1988. So we step out of the realm of detailed calculations to data listings of equipment capabilities. And we just happen to have the copy of Wallace book, basically Wallace Stanley selection and design. Now then, if we open up this book here, open this up a bit, we quickly see, for example, where I'm open up to the section on dryers, and quickly what we see is we have a selection of dryers. We have tray, conveyor, rotary, spray. So we have a lot of design options sitting here. And if I'm trying to dry, say, ceramic towel, I might use a tray dryer. But if I'm drying our friend TiO2 for DuPont, I would want to use a spray dryer. So depending upon how you handle the solids is what dryer you pick. Drying drying calculation is not that difficult. The difficulty in design in this sort of sense is solids handling. How you handle your solids determines what dryer you're going to pick. So you have essentially performance data, product, drying time, various operating conditions, superficial gas. So you have specifications here as to the various process variables that are occurring. And here you're drying a filter cake, clay, sand, TiO2. You can already see the diversity of items here. Whenever you talk about every time you talk about solids, you go up in quite a bit of different diversity type, very, very challenging area. And you come over here and you see these pretty pictures of all these things. In particular, I like to point out that this is a really lousy design. You got to recognize designs are lousy, okay? Yeah. You can get yourself a real lemon of a car. Obviously, three-wheel automobiles were made over the years, but they found out three-wheel automobiles fairly ridiculous, except in France, right? Anyway. This is a particularly awkward and very difficult to use piece of equipment. It's used by the pharmaceutical companies, and you know how great they are. Anyway, what you can do is take this really lousy design and make modifications internally and actually turn it into an excellent design. Right? So with a little bit of engineering judgment and process retrofit, you can take a poorly performing piece of equipment and with minor modifications make it an excellent performer. But I always like to pick up on this thing. Without the internals, it is not a very good piece of equipment to use, right? So then if we go tiptoeing through this book again, right? You have the design specifications for a dryer, what you need to have done for a tray dryer. Here we have various tray dryer types, right? And then suddenly we have performance data. Say we take agitated batch dryer. This is a double cone dryer. And we can see what the performance is when we dry various things, penicillin, Prussian blue, tungsten carbide. So you can see that you try to match what product you have with what sort of variables are over here. And you can figure out what sort of performance you can expect or anticipate from a agitated batch dryer. So, by the way, you probably can't computer simulate this stuff. I mean, it's just the data and information is simply not available. But that gives rise to our buddy table lookup concepts, right? Table lookup concepts. You use what has been documented in the past. And Stanley here, Wallace, right, he spent a lot of effort getting all that data together. I guess to put Stanley up here. He has another book out, came out in '93, where there's 4 or 5 other authors that joined Stanley to write another book. And the quality of the second version was lowered. This is a book that you need to have if you're in the business of design, especially if you've got designs coming at you from all kinds of things. You got to do dryers, you got to do contactors, you got to do mixers, you got to do heated all kinds of stuff. So we have classical, we have table lookup, and basically design engine. When you buy a piece of equipment, they don't design it. What they want to do is use one of their past designs, right? So they don't redesign it, or they might do some modifications, but generally speaking, they want to try to sell you the same design that they have. It's off the shelf. And now we have in the verge these days of computer design packages, and one of the best of those is Aspen, and Aspen is fantastic. Yes, Aspen is fantastic, but limited, right? So what happens is a lot of the processes that are really well studied are and design equations can be written for them. Then you can actually do design using Aspen. An example would be heat exchangers, right? We have Kern's heat exchanger information, but that's not the best. Incorporated in Aspen is what is called the Bell-Delaware method. Kern's book is conservative. In other words, the results of design calculations are conservative, and that usually means you have more area than you actually need for the heat transfer. Bell-Delaware, how can I say this? Bell was a professor at Oklahoma State. And Delaware was the university that did all the research. Let me give you a little bit of the history. Around 1946 or so to about 1960, there was a series of PhDs, students studying how heat exchangers worked. Now, this was funded from industry. You had the DuPonts and the Dows and the Exxons and the Chevrons and Gulf Oil, which you don't know about, and Texaco, which is gone as well. Seven Sisters are collapsing. Anyway, Seven Sisters are... Anyway, go read up on the Seven Sisters, just for fun. So they got together and did a number of PhDs on how to design heat exchanger, or how heat exchangers work. And they wrote up their dissertations. And as most dissertations, what happens to most dissertations, they go to the library of no return. Right, the library of no return. Anyway, Bell in 1980 pulled out all these dissertations, collapsed them all together, and wrote up, I'm not sure exactly what he wrote up, but he started publicizing and talking about the Bell-Delaware method. So if I go back to Kern does an excellent job tube side, and Kern does not do an excellent job shell side. Flow pattern shell side is quite complicated. Aspen has the Bell-Delaware method in it. The Bell-Delaware is primarily directed towards the shell side flows, and hence you get a less conservative design here, and you don't have to over-design, which is what happens up here, and your heat exchangers are more accurately designed, hence you get good performance out of them. And so you have these, Aspen was recently, by recent, the last 20 years, incorporated into, Bell-Delaware method was incorporated into Aspen in the last 20 years. Now, I'm sure there's other ways of doing design, which, basically I think 3 is detailed calculations where you can do the calculation. Now that's probably buried in Aspen. And then you have table lookup for those things that are not buried in Aspen. You must recognize that in design there are very predictable processes. And again, distillation is very predictable. And heat exchange is very predictable. Unpredictable processes tend to be filtration or mixing. They'll work, and then they don't work. So and when you have to shut down your plant, people get really angry, really upset. Anyway, so you must realize throughout engineering, no matter what design you come up with, right, doesn't mean your process follows that design. Right? First point, right, very important. You have a design. You got all the mass balance, all the heat, everything looks like it's really great, and the process doesn't do what you think it will do. It's a fact of life, right? So you have predictable versus unpredictable processes out there. And what happens if your design turns out to not be followed, right, in its application? Then the operations people have to come in and run the process and make changes such that they can get performance out of the process. Okay. Another thing that happens sometimes is illustrated the impact of marketing, right? U.S. Steel Corporation had a really great idea. They had ammonia way back when was selling for 22 cents a pound. And what happened is, we could make a lot of money making ammonia. So they went into a large development making ammonia, and the price, because they entered the marketplace, the price of ammonia dropped from about 22 cents down to 19 cents. And so they went from a profitable process to an unprofitable process. However, they still had to continue to operate because even running at a loss was a lot better than not running at all. At least they were getting some. They were getting some cash flow. They weren't making any profit, but they were stuck in unprofitable land. So the point of the matter, too, with this computer stuff is you can take a look at weather forecasting. Now, weather forecasting is analogous to, say, your design calculations. You're forecasting the weather, you've got a design that you forecast will work, all right? So you can have a situation where you have excellent weather forecasting and you can predict the weather. It works fine. However, at least as far as I know, they're not 100% correct. I'm not quite sure exactly how correct they are, but I would put it around 50%, maybe 40%. Weather forecasting that's the correct level. So you could, if you do an analogy between weather forecasting success and design success, what you predict the plant will do, designs don't necessarily work the first time, okay, or don't work. So then you have such things as the famous 5-year startup. Famous 5-year startup is everything, as you go through the process, everything has to be redesigned. Upper management doesn't like that, I'll tell you. Then design, you really need to also throw in the concept of idiot proofing. Okay, you need to make sure that you have considered the possibility that there'll be some idiots floating around. And this is very you see this all the time. For instance, when you build a nuclear reactor along the ocean, that's not a good idea because of tsunamis, or along earthquake fault lines, and that's probably not a good idea. Or you do both ocean and fault lines, which is the Fukushima mistake in Japan. So you have this business about really dumb designs. An example, nuclear reactors along fault lines, and you're asking for it. You don't want you don't want a situation where you design something and you wind up dead when you run it. And obviously, this question of safety. I have this really great picture of a trampoline. You have a trampoline here, backyard. And then beside that trampoline, you have a fence which has pointy tops to it. Now, in my mind, that's asking for it, right? Asking for it's pretty simple. It doesn't take much of a jump, to know that perhaps it shouldn't be like that. Anyway, so we ran up with this concept that not everything's going to work the first time. First designs may not work. So again, you hand this to the operational people, and they'll make the design work. But if it doesn't work, you need to make retrofits, need changes to the process, and this is typically called retrofits. The retrofits need design as well. And it's also a very big area of design. Example of a retrofit, you're running a crystallization process, and in the crystallization process, you want to pull off the large crystals and recapture the small crystals. So you have a recycle, the flow comes in, the larger crystals go on down, and hopefully some of the recycled crystals come in there. Okay, so that's the typical design for a crystallizer. The idea, though, you come in and you put a baffle right here, baffle plate right here. So the particles have to go this direction. So there's a increase in the larger, coarser particles, and the finer particles have to flow around this baffle and out. So you have a better separation of large versus fines than you did when it was open. Remember, the open was just like that, right? So, this baffle in here, you tack weld it in, and if it works well, you keep it, and perhaps go in and re-weld it really well. If you tack weld it in and it doesn't work, and you don't like it, you take it out. So you have a lot of re-engineering and a lot of process retrofits. I never did correct that one there. Anyway. Design objectives change. Now, the big point here is design is like trying to hit a moving target. Your objectives change on you, and as a result, everything else changes. So there's really no fixed process, and there's really no fixed product. And there's all kinds of reasons for this. Maybe government regulations changed on you. Maybe your competitor has got a new product out. As a result, you have to make design changes. So process retrofits are not taught at university level, nor design changes, right? Hitting a moving target. When you change the objectives on these engineers, they get really sore. They get angry, right? One way you could teach design is use history, right? You should consider using history. how was design done in the past, and we have the car and the airplane as examples of that, or the TiO2 process, or the process to make gunpowder. Interesting enough, the process to make gunpowder during Revolutionary War, the DuPont was making gunpowder for George Washington, and they had explosion after explosion after explosion. So they didn't really have necessarily a very good design. And basically, the old folks knew what they were doing. They accomplished a whole bunch of stuff. So it's very important to recognize the old folks. The old folks were actually very smart, huh? And they didn't have computers. So let's take a look about conceptual design a little bit better, and why should you bother with it. And basically, let's take a few things. Penicillin. Now, people think penicillin's been around for what, 5,000 years? No. Penicillin, which gives rise to the antibiotic industry, right, was discovered. I don't know if discovered is the right word for it, but it was discovered in 1896. And basically it said, oh, look at this petri dish. Something in this petri dish, this mold is killing that bacteria. And 1928, they looked in the petri dish and says, oh, look, that mold is killing that bacteria. And in 1939, they come along and say, oh, look, something is killing that bacteria in that petri dish. And then comes the jump. And the jump was, well, if it kills mold, if it kills bacteria in the petri dish, maybe it kills the mold, bacteria in people. So the jump was made from a petri dish killing bacteria to a human being, and that was the jump that was made. This back here, that jump was not made, nor was it made there. And so in 1939, they didn't have, and they went full-scale production into fermentation tanks or whatever. They grow penicillin in, which is large tanks. And by World War II, the invasion of Normandy, D-Day, and that sort of thing, they may have had 2 million doses of penicillin on hand for the wounded. So penicillin actually is the second best kept secret of World War II. Kind of interesting. And from penicillin, then they found other things, and then they found other things. So the whole antibiotic industry blossomed forth from just that jump that was made by Pfizer Corporation. Nobody talks about this, right? However, there is the statement made, I don't know where I heard it, that Napoleon's soldiers ate moldy bread during the Napoleonic Wars in Europe. Napoleon was marching around. Anyway, if they were wounded, they would eat moldy bread, and that would help them heal quicker. Now, the point is, the moldy bread may have actually contained various types of antibiotics, and as a result, saved a lot of soldiers there. We should also recognize the Wright brothers, air travel, invented the airlines, that sort of thing. One of the interesting things about the Wright brothers is they eventually got their flying machine built and working, and so they went to the Army for more additional funding. And they couldn't very well go to the Air Force, could they? So they went to the Army for funding, and they took the captain up and promptly crashed the plane and killed the gentleman. And the captain was promoted to major, as if he cared at that point. Then we have cell phones. Cell phones actually were around in World War II when you landed the Marines on those islands In the Pacific, they had walkie-talkies. At least that's what that shows in the TV movies, talking to each other. So walkie-talkies, basically cell phones. When they started doing cell phones, the size of them was the size of walkie-talkies. And now, because of the cell phone craze, we have all these lovely cell towers throughout the land, right? Cell towers throughout the land. Design tools can consider using the scientific principle. There's counter to scientific principle. There's the engineering principle. And then failure is a wonderful thing. And then we'll throw in discoveries and happy surprises, analogies, and juxtaposition. So those are some design tools that are out there. So let's go back and talk about the scientific principle. The idea is you make a hypothesis. You think and think and think. Got your theory, think of making a hypothesis, and then you make some predictions about what your equipment is going to do. So then you run your equipment and check your hypothesis your predictions against your hypothesis and see if you can't correct the hypothesis. And this is really a very inefficient way of doing it. First off, I don't think you're, generally speaking, given the problems that engineers face, I don't think they're smart enough to make good hypotheses, basically. They don't know enough about how the equipment runs or how the process occurs or whatever. And as a result, there's an awful lot of effort that accomplishes nothing, right? All I can say is, in my opinion, the scientific principle is highly inefficient. And design around is not considered. You probably never heard of design around. Give you an example here. Well, let's put it like this. Very important point. You got to have the right perspective on the job, right perspective on your piece of equipment, right? You need to have the right perspective. If you don't have the right perspective, your design is going to fail. Like the red dye process failed in making color durability plastics. So obviously they changed their perspective. They learned more. Now then, the best, you probably never heard this before from a college professor, especially an engineering college professor. Right? How dare you? If you have a difficult problem, avoid it. Oh, heavens. Isn't that cheating? That's another shock to students to find out that oftentimes very difficult problems, you're not going to have very much success in solving them. And the best way is to ignore them by doing a design around. If I take a 3-wheel all-terrain vehicle, and you will notice quickly that it's unstable. So I try to design around the instability of a 3-wheel vehicle. Take a child's tricycle, for example, right? Draw a tricycle here. And it has a tip-over mode here and here, right, going forward. And quite frankly, it's a difficult problem. So you don't do it. You don't try to solve that problem. You go ahead and make all your all-terrain vehicles 4-wheel, which is stable, and you don't have the problems of tipping over, right? Again, it's the idea of gaining a proper perspective on your problem. If you have a proper perspective on your process, then you can use it to very good advantage. Trial and error, engineering principles. Actually, I don't like the words trial and error. Perhaps you need another name. You build it and see if it works. You build it and see if it works. Build it and see if it works, right? You don't make a hypothesis. You're just sort of guessing. And it's a learning process. And quite frankly, I think it's quite much more rapid than the scientific principle idea. And as we will get later, trial and error will follow the different levels of education, which I'll talk about a little later. What's really interesting, and people who know everything, usually they don't know everything. And what's intriguing about this scientific principle, what was I going to say? It was definitely profound, but I've slipped what I was going to say. Oh, yes. Right here. Let's go back. Back here with the scientific principle, right? Think about it. You're Edison, Thomas Edison, and you're trying to figure out what filament you're going to use in a light bulb, right? So what are the qualities? Did they know enough about material science and current flow to understand the physics involved with light generation from a filament? I mean, stop to think about it. 1880s, they haven't really discovered photons yet, right, perhaps, nor could you relate photons coming off to something physical occurring in the filaments. Just think about, see, you're not smart enough to make a good hypothesis, and light bulb filaments is a good example of not being smart enough. See, the scientific principle implies that you can make a good hypothesis, whereas no, not so much. Anyway, so up here we mentioned discoveries. Discoveries are concepts, products, and processes that are searched for. You make discoveries by searching for them, right? In a sense, this combines searching with proper perspective here. It's often said that Columbus discovered America. Okay, he searched for America, and he discovered America. Right, so that's an example of a discovery. Now then, let's throw in the proper perspective on Christopher Columbus. It is very true he discovered America. However, he was probably the last person to discover America. See the difference in the perspective? From the perspective of Europeans, he discovered America. From the perspective of everybody else in the world, he probably didn't. There's obvious evidence of the Vikings being over here. There's evidence of the Chinese actually making it to the Grand Canyon. I don't know if that's actually true or not. And then, of course, you have the Native Americans, which, unfortunately, in a very real sense, they discovered America as well. They came in from a land bridge, so I'm not quite sure that, everybody comes from somewhere. Right? So this is the idea of proper perspective. You got to look at things in the way they actually are. Right? Three-wheel tricycle will be made for children, but they will always have this problem of tipping over, and you will always have skinned chins and a little bit of crying and maybe a couple bruises on the arm. That goes along with tricycles. I guess it's learning, teaching the child that life's a bit on the tough side. Anyway. Now, I make a difference between happy surprises and discoveries, right? Whether you really want to do this or not, it doesn't bother me. But happy surprises occur because you didn't search for them. It's sort of like a surprise birthday party. People don't discover their birthday party. They are surprised by their surprise birthday party. So surprises occur without you searching for them. They're sort of like, hey, I'll give you this. Nature says, hey, I'm going to give you this. And it occurs all the time, and it's not properly emphasized. Examples is the Post-it notes adhesive, right? 3M haphazardly fell on this adhesive. They had a research program, good, but this was totally a surprise to them. Aspartame was a surprise, right, for them. Aspartame was an artificial sweetener, equal, developed by Searle Corporation, and it was just by chance that it was discovered. Then we have our friend penicillin. Surprise. The surprise was penicillin kills bacteria in a petri dish. So you find that luck plays a very key role in development, and we have the idea that luck visits those with a prepared mind. It's very important to have a prepared mind. So that's why you actually have education, is to be prepared for what nature will give you free as a surprise. This is a quote, I think, by Einstein, but I'm sure this has also been expressed many times by many people over the many years that humans have been around. So luck, how sometimes viewed as not going to be scientific, right? Luck's not scientific, but it is. Whatever luck has provided you is basically they obeyed the laws of nature. Laws got to be plural. Laws of chemistry, physics, and biology, as does everything else. So it's just that you weren't smart enough to see it coming. Oh, heavens, I'm telling people that they're not smart enough. Yes, that's very true. And politically correct is not that. That's not politically correct. So the other thing is you recognize failure has a steep learning curve. The quicker you learn, the better off you are. So it's sort of a wonderful thing. So again, I was saying penicillin, airlines, cell phones. I was supposed to discuss penicillin, Wright brothers and walkie-talkies. I already did that, so we can move on. Analogies. Kind of interesting in juxtaposition. The Wright brothers watched birds fly. And by watching birds fly, they figured out how they should build their airplane. In particular, the Wright brothers could get off the ground. Eventually, they could get off the ground, and they could go straight. So the Wright brothers could get off the ground and go straight. The problem is the Wright brothers couldn't turn the airplane. That was their next challenge. They could only fly straight. So they sat around watching birds fly. So you have this here bird, and they noticed that birds turn by lowering this wing and increasing that wing. And what that did was change the lift vector from here to here, or here actually. And as a result, they had a turning vector up here of sorts. I'm sure this is wrong and it's a good explanation maybe, but you take one of those engineers, they'll tell you it's wrong. Maybe, I don't know. So they didn't have to do any necessarily research on this. They just made observations, right? They didn't plan any experiment. They just observed. Now, if you get out and watch birds fly, actually they fly in very different ways, right? They fly in very different ways. Now, the tilting of the wing, if you get a bunch of buzzards flying around, you'll notice that they fly in circles by having the inner wing dip just a bit. Anyway. So you can go a long, long way with analogies, and you can juxtaposition. And these are not very well taught in engineering as well. At least I don't think they're taught very well. So let's go through some of these just for fun and see what happens. I move this like this. Some examples of juxtaposition or analogies. Unloading bananas. Now, this is not the small bunch of bananas you'll see in the store. This is the big bunch of bananas, right? So, a chap named Harrington was watching bananas unload in Miami, Florida, and he looked over at it. He said, if he could do that with bananas, he could do that with people. And he had a large quantity of land around Sun Valley, which he wanted to develop into a ski resort. And he needed to get the people up on top of the mountain easily. So he drew the analogy between bananas unloading and a ski lift. In fact, the design almost fits exactly. Banana bunches like this probably weigh as much as a small human, or so. All he needed to do was change the banana hook into a seat, and away he goes. So again, the ski lift was invented in Miami, Florida, where there's no snow. Now then we go over here and we say cars and cattle. Well, it's speculated that, let's explain cattle here. You bring in a cow, you hit it in the head, put it on a hook, probably drain its blood, and then further on down, you remove the skin, then you start sectioning it up, and eventually you get the steaks and the ribs and the ground meat and whatever. Now along comes Henry Ford and watches how they take apart a cow, and he exchanges that he said, if they could do that with a cow, they could operate in reverse direction and build a car. Taking all the small car parts and moving along an assembly line, they could assemble a car, just as they deassembled cows. So there's an analogy there as well. Then we get into the electric hand drill. Basically, the history here is Stanley. No, not Stanley. Black. Mr. Black was drinking whiskey with Mr. Decker in someplace in Ohio. Everything sort of happens out there in Ohio land. Anyway, they had a gun on the table. They were drinking whiskey. And we don't know which one came up with it, but they looked down and they said, well, we could develop a hand drill, put the motor like where the bullets are and whatnot. So there's a direct analogy between a gun and a hand drill, so to speak. Then we have the famous dancing snakes, right, in organic chemistry. Organic chemist, very famous, I don't remember his name, he's trying to figure out the structure of the benzene ring, and he had 6 snakes dancing around in his head. And they danced and danced in his head. Then suddenly out popped the benzene ring in his dream. And when he woke up, he had his problem solved. As coming up with the structure of benzene ring. There's creativity here, some, but also analogies and juxtapositions are hard at work. Now, what also happens is actual design. Take the food industry and the pharma industry, they have similar problems. They don't compete necessarily, but they have similar problems. So they have the same problems, same design solutions. Maybe they have the same packaging methods. So this is the idea of analogies and juxtaposition. And what happens is they jumpstart your design, right? Jumpstart your design. And in here we have the engineering method is best. Well, the bottom line for engineering, if it works, why bother proving it? What is there to prove? Oh, such an anti-science statement. Huh? An example of this is we have the electrical engineering professor named Heaviside, who would solve his differential equations, and it would really make the mathematicians very angry. And the mathematician says, you can't do that. There's no mathematical theory. And Heaviside would take his answer and plug it back into the differential equation and say, see, it works. So Heaviside's method was basically the Laplace transforms. Now, if you take a look, engineering, take something that works and improve it. That's often what happens. And then we get along down here into the area of misapplications. Now, you've probably never been told to misapply stuff. And if I go up here, and if I have something unloading bananas, I misapply it into a ski lift. That's one way. But anyway, when you get down here, misapplications can be a great concept. All right. I've done this myself in one calculation I was doing. Oh, you're not supposed to do it that way. And the response back is it works. So if it works, use it. So oftentimes misapplications can be quite useful. Again, the prime example would be up there. Bananas, I bet the first designs for the ski lift was from Banana Designs. Now then, let's talk a little bit about people. Design people are driven people, right? If you take a look at Steve Jobs, Wright brothers, Henry Ford, they're probably driven people. And you take your typical college student, very few of them are driven. I met a chap who gives some signs. He wanted to do serious chemistry, and he wanted to use. I don't want anybody around here doing serious chemistry because a professor at college level, I don't want anybody killed. One of the most dangerous things that often happens in chemistry classes is you have an undergraduate student, maybe a freshman, coming up to you and having a beaker that's boiling, saying, what am I supposed to do with this? And two of my acquaintances, professional acquaintances, only had 3 fingers, right? And basically, he had his thumb and his finger. The rest of the hand was blowing away. Now that's an example of a freshman coming up with a beaker, saying, "What am I supposed to do with this?" And he hands it to the TA, which is a guy really dumb to take it, and he got his hand blown apart. So driven. College students aren't particularly driven, except for this one chap, and I don't want to have him do actual chemistry around here. You want to be able to do chemistry safely. My uncle was an organic chemist inside Eastman Chemical, and basically, as he had his face was all scarred up. And his old age, when he was 50 or 60 or 70, the glass shards came out of his face. From old explosions that buried glass into his face, and they never really got around to digging him out. And they came out when he got older. It's kind of interesting. So you find out that these design people are not nice people. They are not nice people. Many of them are contrarians. They're not going to accept status quo. And they're probably not going to be well liked. So your problem in the RED project is to make your design students driven. Somehow you got to realize you have to have driven design students. Somebody is committed to the cause, so to speak. You should also recognize that design is boring. You take the design calculations inside Kern, for example, It's an iterative process. It's very seldom if it's one time and done. Usually you have to do a design, then you do a redesign. Design is done over and over again. You have boring, lengthy, detailed, exact calculations. You're tweaking this, you're tweaking that. So design, for the most part, especially design with established calculations, is boring. That's why you throw it on a computer. And good idea, throw it on a computer. And actually, this should be split apart. You want to design your competition. You want to pull that off and make that another subsection yourself. Design your competition. See what their capabilities are. See how your process is better than theirs. See how their process is better than yours. So you get some sort of information gain when you're designing the competitors. And for example, if we have one of those alien spaceships that land, I'm expecting one soon, right? We can go in and design, reverse engineer their spaceship, figure out how they fly. I suspect, from what I've seen, the technology, or what has been stated, their technology is far superior than ours. Oh, heavens. So let's pick up on computer simulation again. Computer design methods. Useful, but there's a serious question about how useful. The real problem with computers is they removes the design engineer away from the process. You're not intimately involved with the process. And of course, we recognize that designs often do not work, right? Not documented as to what their performance would be, right? You got to evaluate performance, you got to have a performance index. And then to evaluate that, you got to have predictions of what's going to happen. You might establish performance indices as you tweak stuff from this to that. During tweaking, you might develop performance indices. Users make improvements. Again, this might be retrofits. One of the nice things about table lookup is already you have the performance indices already there. It's just that they're not called performance indices. Now here it is. I promised you the different levels of education. And actually, in a true sense, this is the way the design works. Design follows the level of education. First, you start out with not having a clue. You walk around clueless. Clueless. Hi, my name is Clueless. Now, that's a really sad state of affairs to be clueless. So the next level is basically the idea that you recognize that you don't have a clue. You recognize that you are deficient. So then you go out and gain knowledge. That's really great. Gain knowledge. However, knowing something and understanding it are two different things. You can gain a lot of information, but if you don't understand it, then there's significant problems there. And then following understanding comes wisdom. So, in a sense, design is a form of education, right? If you take a look at the university education, it's extremely limited. First 2 years is taken up with calculus and light, what I would refer to as light courses, English. But the last 2 years is where the more serious stuff takes place. And if I do 30 weeks a year, 2 years, I get 60 weeks. And if I take a look, if I have a serious student, maybe the student will work 40 hours a week for 60 weeks. I get about 2,400 hours. Now, really, you take, say, a student who works 5 hours a week, you get, what, 300 hours? So you can see differences in our student performance between 300-hour student and a 2,400-hour student. The problem with the 2,400-hour student, it's scattered about, right? Scattered about. Got a little bit of history, you got a little bit of chemistry, you got a little bit of this, a little bit of that. So in a real sense, real education starts to occurs when you're employed. Employee. And if you read Malcolm Gladwell, excellent book. Excellent books, I should say. And one of his books, he says he figures that to become a pro at something, you need to put in 10,000 hours of concentrated effort. I mean, Tiger Woods did not get created overnight. The Beatles did not get created overnight. Right? So Malcolm calculates that the Beatles put in at least 10,000 hours before they hit the big time. Right? Before they hit the big time. Now, why do design? Well, design makes money and profits, and that's really, really good. Really, really good. So we also have this business about human interaction. NIH, National Institute of Health, or not invented here. If I didn't think of it or develop it, then it's not important. And egos, oh, geez, these egos are huge. I know everything, you're dumb, right, type things. Actually, my perspective on things is I want to learn from everybody. I forget the caste system that is around in academics, and I try to focus on learning from everybody. In other words, I'll bring coffee and donuts to the third shift at 3 a.m. in the morning. When you bring coffee and donuts to the third shift and you talk to the operators at 3:30 in the morning, they will tell you what the first two shifts are doing wrong. Right. What the first two shifts are doing wrong. And I'm going to toss this out. This can create a lot of controversy as well. The myth of the expert. Are you an expert? You got to prove it. So here we got one expert. There's one expert. And over here we have another expert. And the two experts. You ever notice experts when they get together, they're going to argue? I've never seen two experts get together where they agree. They always have some sort of argument. And if they have an argument, that means they have differences of what they think. And it could be that one of them's wrong and one of them's right. It could be that both of them are right, both of them are wrong, or one of them's right and one's wrong. But if one of them's wrong, then why is it called an expert? So I call this the myth of the expert. There's so many experts out there. You go into a courtroom and an expert witness, you'll get one witness saying one thing, who's an expert, and you got another witness saying another thing, which is just the opposite. So under a set of circumstances, you have two expert witnesses, but the problem is if they disagree, they are opposites to each other, then one of them's bound to be wrong. And if one of them's wrong, why is he an expert? I tend to view things that you better be a student. You always want to continue to learn. It's very important to continue to learn. Right. You want to continue to learn. I mentioned obtaining a proper perspective on things. right here, when you design your competition, you are changing your perspective on your process when you're designing your competition's process. Anyway, minor detail. Now, I think you should have an entire course dedicated to design mistakes. I love it. Design mistakes, fantastic. Now, a really good source of design mistakes is, of course, NASA. Now, NASA is a fantastic organization. There's no doubt about it. But the mistakes they make are, super, super fantastic mistakes that you can learn from. All right. So design mistakes are many, many, many. Right. Even computer design can be bad designs, right? Just because you have a computer do it doesn't mean it's going to be right, or if it actually occurs. I like this one about the Comet airline. You probably never heard about the Comet airplane. It was the latest and greatest, and what was unique about it is it took off but never landed, often never landed. And what happens is when they had the airline, I can put it up here, you had windows here. And the airplane crashed because of their window design. That's absurd. How does windows crash an airplane? Well, the problem with this is that these windows were a bit too squared. And what would happen is the stresses would concentrate right at that corner. And then the stresses would concentrate at that corner, and the crack would form between the two. And again, for this window, windows, there would be a crack along the top of the windows along the plane. So after it took off, the top, 30,000 feet, often the top came off. And at 30,000 feet with the top of the airplane coming off, there isn't very few people survive. So I think the RED project should end with a design book. Topics above could be chapter titles. Like you could probably spend a whole chapter on human interactions. You could spend another chapter on design mistakes. And young people can learn from design mistakes. Anyway, let me stop here, and since this is a videotape, I don't have to answer any questions. And I wish you good luck in your pursuit with the RED project, and I will sign off now and stop. And you have a good day, rest of the day, and good luck and happy designs. Bye-bye.